Good morning, sir.
Good morning. Is my screen visible?
Yes, sir.
Yes, sir.
Yes, sir.
And so, yeah, okay. Are there any questions, doubts? Hello. Is anyone having any question, doubt?
No, sir.
Okay, so then let me start. So last class I had discussed an example how to develop the element level governing equations and then how to solve a problem for the two noded truss element. So yeah, is my screen visible?
Yes, sir.
Yes, sir.
Okay. So today let me discuss a little bit more on 2D elements and emphasize more on the compatibility conditions. So as an example, I will take a 2D element example as the plane stress plane strain elements. The idea is to actually discuss the compatibility requirements, and so that we have some background for the plate bending elements when we talk of compatible and incompatible elements. So plane stress, plane strain elements. So now in this, no, these are 2D elements. That is what I am going to discuss, and maybe it might be again some kind of a revision for you. But let me just briefly discuss about this. So what we are talking about here is that we have a let us say a body with certain thickness. So let us say the thickness is h, and in the plane of the body these are the coordinates, say x, y, and z is along the thickness direction, and all the forces are no in the plane xy plane. So whatever forces are there either on the boundary or on the whole body, those are on the xy plane only. So these are the forces. So in this for the plane stress case, plane stress h would be, h is very small compared to in plane dimensions. So that is dimensions along x and y compared to in plane dimensions. And the plane stress situation would be arising, plane strain. Plane strain would be arising when h is very large compared to in plane dimensions. Compared to in plane dimensions. Yeah, these are the two cases. So we will be discussing both of them together. Only difference is in the constitutive relation actually. So plane stress, as you know, these stresses sigma zz, tau xz, and tau yz. These would be 0, and in the plane strain, as you know, these epsilon zz, gamma xz, and gamma yz. These would be 0. So that's the basic thing. No, when we talk of plane stress and plane strain elements. So now if we say basically let us say the displacement displacement field within the body. So we will have two independent displacement along x and y. X and y are along the in plane dimension, and z is along the thickness. So u will be function of x and y. This is the displacement along x, and v would be the displacement along y direction. So this is along y. So these are the two primary variables. Now we are going to work with these variables, and these are also the primary variables for the problem. Now if you look at the strain, so the strain epsilon xx is del u by del x, epsilon yy is del v by del y, normal strains, and the CI strain gamma xy is del u by del y plus del v by del x. And when it comes to the stresses, so when I talk of stresses, so we have to we have basically, because we want to work in terms of displacement, so from displacements we calculate strains, and then we express stresses in terms of strain. So we need the constitutive relation, stress strain relationship. So we assume that the material is linear, elastic, and isotropic. Linear, elastic, and isotropic. Material. So now for the plane stress case, you will have, if we express the stresses in the form of a vector, so we can say sigma xx, sigma yy, and tau xy. This is equal to a constitutive matrix, which is E upon 1 minus nu square, where E is Young's modulus, nu is Poisson's ratio, as you know. So this is 1 nu 0, nu 1 0, 0 0, 1 minus nu by 2, so that you get G into epsilon xx, epsilon yy, and gamma xy. So we can also put this in the vector in this form, symbolic form. Sigma is equal to C into epsilon, where sigma is this, C is this, and epsilon is this. So this is for the plane stress. Now you know this relationship, that these three stresses are expressed in terms of three strain components: epsilon xx, epsilon yy, and gamma xy. Here C is known as constitutive matrix. Somehow it is jumping. Yeah. Am I audible? Hello?
Yes, sir, you are audible.
Yes, sir.
Okay. So C is constitutive matrix. Constitutive matrix. Okay, and for the plane strain, the relationship is going to be the same. That is a relationship between sigma xx, sigma yy, tau xy, and epsilon xx, epsilon yy, and gamma xy. So only difference is that constitutive matrix C for this case would be E upon 1 plus nu into 1 minus 2 nu, and then 1 minus nu 0, nu 1 minus nu 0, 0 0, 1 minus 2 nu by 2. So this is the constitutive matrix for plane strain case. Now we look at the No, because no, the whole thing is based on, we are going to discuss the formulation based on the integral functional. So next is total integral functional. Integral functional or total potential energy functional. Total potential energy functional. So how do we write? It will be consisting of, as we have been doing. I am not starting here no, with the differential equations, but directly writing the integral functional. So this I will be consisting of strain energy, and the strain energy no, per unit volume is half of sigma xx epsilon xx plus sigma yy epsilon yy plus tau xy into gamma xy, integration over the volume. So because no UV are constant, and so also the epsilon xx, epsilon yy, and gamma xy constant through the thickness. So we express this integral as half integration over area and h into sigma, h is the thickness, sigma xx into sigma yy plus sorry epsilon sigma xx into epsilon xx, sigma yy into epsilon yy plus tau xy into gamma xy dA. So this is the strain energy part. Here no, the either the plane stress problem or plane strain problem, in both cases the non-zero pairs of stresses and strains are these, sigma xx epsilon xx, sigma yy epsilon yy, tau xy and gamma xy. And then you have this
Sir,
potential of the externally, yeah,
sir, I have one doubt regarding the plane strain condition. So,
yeah.
in plane strain, like our strains will be zero, but stresses will be there, right?
Yeah, correct. Yeah.
So if we want to write sigma equal to c into epsilon,
Yeah.
in that case, like sigma will have total 6 components.
Yeah. But yeah. So I am writing here the the independent components of stresses. Yeah, you will have even in both cases for linear elastic isotropic material, tau xz and tau yz, gamma xz and gamma yz will actually be zero in both cases. So only thing, in case of plane stress case, sigma zz is zero, epsilon zz would be non-zero. In case of plane strain, sigma zz would be non-zero, but epsilon zz would be zero. So, but the independent pair of stresses and strains are only three. That is sigma xx, epsilon xx, sigma yy, epsilon yy, tau xy, and gamma xy. So I am relating only these three.
Okay, sir.
Yeah. Yeah, so this is the strain energy part, and then the potential of distributed forces. So let us say we have body forces acting on the body. So the integration again we can write as the integration over area into thickness. So that is, h is the thickness, let us say. And then you have displacements UV transpose. The body forces are FBX and FBY, body forces along x and y direction, into dA. So let us say that only these body forces are there. Even if the boundary forces are there, you can account for that. So if, let us say, the boundary forces are also there, then the integration over the boundary. So you will have UV transpose, and let us say the boundary forces, the forces on the boundary of the element are Tx, Ty, and ds, where s is the length along the boundary. So this is the integral functional. We can rewrite this as half of integration over area and this h, and this quantity can actually be written as sigma xx, sigma yy, tau xy transpose into epsilon xx, epsilon yy, and gamma xy dA, and the other two terms, so minus no, the other two terms as it is. So if you look at, finally we can say that this would be half integration over area h, and this is sigma. Sigma can be written as C into epsilon. So finally we can write this as basically epsilon transpose into C transpose. C is symmetric, so C transpose is same as C into epsilon dA, and minus of course these terms H into UB transpose into FBX FBY dA minus integration over boundary UV transpose Tx Ty ds. So here, FBX, FY, FBX is the boundary force per unit volume along x direction. FBY is the body force per unit volume along the y direction. Tx, Ty are the boundary tractions, that is force per unit length along x and y direction. So these are the traction forces per unit length of the domain or the element. So now, when we talk of the finite element formulation for this problem, finite element formulation. So we need to make important thing is the approximate solution. So when we talk of approximate solution, again we have those the four conditions which I just repeated again. So one is the differentiability. Differentiability requirement that states that whatever approximate solution we assume for u and v, that should be differentiable up to the highest order derivative highest order derivative present in this case integral functional. So highest order derivative of u and v is first derivative with respect to x and y. So whatever approximate solution we assume for u and v, it should be differentiable at least once with respect to x and y. So that is the differentiability requirement. Then the completeness, that means whatever is the highest power term present in the polynomial approximation of u and v, the lower all the lower order terms, lower degree terms should be present in the function. So that is the completeness requirement. And the third is the inter-element compatibility. So now this says
Hello,
that,
sir.
yeah.
Sir, in integral that equation, the second term and last term, third term, how we can write that means expression u b transpose into body force means that body force.
Yeah, so you are talking about the body force or this traction forces Tx and Ty.
In both the cases, how we can write that u b transpose into that body force means
Yeah, so
how it will
it will
calculate the
be, say it will give you u into fbx plus b into fby.
yes
So
sir.
see, H is already there, so fbx into dA will be the force over a differential area dA along the x direction multiplied by u will give you the work done, and the potential is negative of the work done. So the total potential is going to be u into fbx plus b into fby. So that is what is written as UV transpose into FBX FBY. So that it gives you U into FBX plus V into FBY. So we have already, for the 1D problems, we have
Yes,
already discussed the interpretation of
yes,
these terms. No?
yes, yes.
Is
Okay.
Sir,
it
but
clear?
Thank Yes, sir.
sir, but the total product will be like h is
So see,
also in h will also have the dimension of length, right, sir?
yeah, HEC, that's what the FBX FBY
Ah,
are the forces per unit volume.
yes, sir. So u and v, are they like they are also
They
they
are
will
they
also
are
have the
the,
unit of length?
yeah, they will have the unit of length. So that is why now why it is potential, which is work done. So work done would be Newton meter, no? See, this
Yes.
FBX would be Newton per cubic meter, then multiplied by HDA will give you Newton, and into displacement will give you it in the work done in Newton meter.
Yes, sir.
So inter-element compatibility is meaning that primary variables, so in this case u and b, should be continuous across the element boundaries. So like in 1D we were talking about, no, the primary variables should be continuous across the elements. Here we will have the boundaries. There in the 1D elements, the boundaries across the elements are points. Here they would be lines in 2D, and in 3D these are actually surfaces. So in 2D the u and v should be continuous across the element boundaries, element interfaces. So that is the inter-element compatibility. And then we will have the additional thing in 2D and 3D problems is geometric invariance. Geometric invariance. So now geometric invariance means these three, the first three were there in the 1D also, I discussed those. An additional thing is geometric invariance. So that means when we write an approximate solution for the variables, so if we interchange say x and y in these 2D problems, the form of approximate solutions would not change. And if it is if we interchange x and y, if the form is not changing, means the approximate solution is geometrically invariant. So these are the four conditions which should be satisfied by an approximate solution. So let us say for this plane stress, plane strain problem, what are the possible elements? So now if we look at
Hello,
finite element,
sir.
yeah,
So
yeah.
why it is important to be the element geometric invariance, sir?
Now see, because we are formulating an element, and a priori we do not know that the displacement, whether it is going to be how it is going to vary along x and y. So we assume that the variation or displacement along x and y is similar. So for that we require this geometric invariance. So that the and the ultimate goal of all of these requirements is that finally when we keep on increasing the number of elements in the discretization of a domain, so ultimately the solution tends to exact solution. So to make it for that we require these conditions. And geometric invariance, as I said, is to make sure that we have the same variation of displacements u and v in the x and y directions. It should not happen that one side you have quadratic and other side it is linear. So we don't want that kind of a thing. Either it is linear in both sides, or bilinear and or quadratic in both sides.
Okay, sir.
Yeah. So now if you talk of finite elements, the simplest thing you can think of in a 2D element is a triangular, and the formulation is let us say in the physical coordinate space. So this is a triangular element, and we have x and y. The nodes are, this is node 1, node 2, node 3, and at any point the coordinates are x and y. And this is no, the node means for to satisfy the inter-element compatibility, we know that the primary variables should be there as degrees of freedom at the nodes. So the nodal coordinates would be x1, y1, and the corresponding displacement nodal degrees of freedom would be u1, v1. Here the coordinates would be x2, y2, and the corresponding degrees of freedom would be u2 and v2. This is x3, y3, and corresponding degrees of freedom would be u3 and v3. So this is the simplest thing we can think of, and in this case how we will assume is, we will assume the approximate solution u within the element. Now see, in a triangular element, we look at the differentiability requirement. So differentiability means as per the integral functional u and v should be differentiable at least once. So for that means we should have linear term in x and y, and if we have linear means constant should be there from the completeness requirement point of view. So we can have this as say a0 plus a1x plus a2y. So now if you see, this meets the differentiability requirement, that it is differentiable once with respect to x and y, and it is complete polynomial, and it is also geometrically invariant, because if we interchange x and y the form remains same. and we have to check whether it satisfies the inter-element compatibility or not, so that we will check. And so similarly you assume an approximate solution for V, so that is say B0 plus B1x plus B2y. Okay, so this is the approximate solution. Of course, the next step,
Sir,
I am not going to discuss the complete steps for this. Yeah,
sir, you said geometric invariance mean if we interchange the x and y in the expression of u and v, then it's
yeah.
remains same. But
It,
I-
its
but sir,
form
I have
remains.
also
Its
yes
form
sir.
remains same. Its form
Ah,
remains same.
yes, sir. Form remains same. But sir, I also read that the shape function for displacement and the position that's as same. That's we call geometric invariance. We can
No,
use same.
that is isoparametric formulation. So when we
Okay,
talk
okay.
of formulation in the natural coordinate system, I'm going to talk about that. So when we talk of formulation in natural coordinate system, then if the order of or the degree of polynomial for approximation of displacements and the geometry, that is xy coordinates, is same, then that is isoparametric formulation.
Okay, sir. Thank you.
Yeah. So now this is the approximate solution. Of course, the steps would be, I presume that you have done a basic course on finite element. So the further steps of formulation, you know that A0, A1, A2, you have to express in terms of U1, U2, U3, B0, B1, B2 in terms of B1, B2, B3. So you can write UV in terms of area coordinates and values of U and V at nodes 1, 2, and 3. Then put into the integral function and all of the element level governing equations. So what I am going to talk here is whether the compatibility condition is satisfied or not. So for that, let me take a domain, let us say rectangular domain, and that is discretized into 4 triangles. So let us say this triangle and this triangle and this triangle. So 4 triangles, and these are the nodes. And let us say that this is element 1, this is element 2, this is element 3, and this is element 4. And this is the common, no, we have the common boundaries between 1 and 2, 2 and 3, 3 and 4, 4 and 1. So let us take common boundary between 1 and 2, from A to B. So this from A to B is the common boundary. Now the compatibility requires that if we work out say U or V along line AB from element 1 or from element 2, the two must be same, and if it is same, then it satisfies the inter-element compatibility requirement. So now let's look at how the whether the compatibility conditions would be satisfied or not based on this approximate solution. So if you look at the line AB, so line A is a straight line. So then we can write, say, y is equal to either y in terms of x or x in terms of y. So y equal to, let us say, mx plus c. You can write, no, because when we are moving along line AB, so we y and x have to be related. So let us say y equal to mx plus c. Then if I look at variation of u along AB, of course, no, the constants A0, A1, A2 would be different for element 1. Constants A0, A1, A2 would be different for element 2, and similarly B0, B1, B2. So I'm just writing for a general case that U along AB would be, say, A0 plus A1X and plus A2 into Y, but Y is MX plus C. So then you can, as you see, you can write it as A0 plus A2 into C is a constant term, and then plus you have A1 plus A2 into M into X is a linear term. So you can see from this that you variation of similar thing you can write for V. So the variation of U along AB is linear in X. So now if variation of U along AB is linear in X, so we already have, say, at nodes A and B, because we have the degrees of freedom, same degrees of freedom from both for both the elements. That is at point A itself, node A, element 1 and 2 would have same values of U and V, and similarly at node B, element 1 and 2 would have same values of U and V, and then in between the variation is linear. So that values at two locations are already common. So in between, since the variation is linear, so it would be common and that for therefore it will give you the same variation. So that means when I plot, let us say u no u along AB, along the length along AB. So let me say SAB is the length along AB. So it would be the variation will be same, it is linear. So this is point A and this is point B, and you will get this variation from element 1 as well as from element 2. So that means the inter element compatibility will be satisfied, because you know the variation from A to B is linear, and you can have the unique linear variation from A to B, because at A and B both the elements 1 and 2 have same values of u, same values of v, and in between it's a linear variation, so it would be same. So that means no, the element is compatible. So this triangular element is compatible. Now if similarly if you go for next level is you can go for 6 noded triangular element, you will find that that will also be compatible. And so this is about the triangular element. So now let me talk of rectangular element. So let us say 4 noded element. So I am only talking about the, so is the compatibility clear how it is compatible?
Sir, I could
Hello.
not understand the last part of, like, how did you conclude that through the graph that this is
Yeah,
compatible?
so
Like,
I am
it is a
saying,
linear.
see, I am saying that variation of u or v along AB is linear in X, right? So the variation of u, if you plot along line AB, it is linear, and it is going to be linear in both elements, element 1 and 2, right? Now at A and B, we have already values of u and v are same for both the elements at node A, and similarly values of u and v are same for both the elements at point B. So at A and B, both the elements have same u and v values, and in between the variation is linear. So from these two values at A and B, we when we plot a linear line, no, have a linear relationship. So both elements will give you the same no u and v values. So that is what I said, that at A u and v are common between both the elements. At B also u and v are common between the two elements 1 and 2. In between the variation is linear. So whether we talk of element 1 or talk of element 2, it would be the same linear variation.
Sir, so
So
if
that is how
it
u and v values along a line AB will be same whether we get it from element 1 or element 2. And if it is so, then the element is compatible.
if it was non-linear relation, then will it not be the same?
No, then it will not, yeah. So if it was, let's say, quadratic, let us see if it was quadratic, but we have only two values common at A and B. So quadratic expression cannot be, a unique quadratic expression cannot be fitted based on the two values. We require three values, and three values are not common. So it will not be then unique. It will
Okay,
be, then it will be incompatible.
okay. So basically, the minimum number of nodes we will require for non-linear element, if those are present, then we
Yeah,
can tell that if they will be compatible or not, right?
yeah, right, right. So
Here we
for
are
example,
short of one element, one
yeah,
node, right?
yeah.
Okay, okay, sir.
So now if you look at, yes, anybody else?
Yes, sir. So can we say that while writing the shape function for element one and two for the node A as well as node B, so for both the element the shape function will be same, sir, or not?
That depends on the sequence. I'm not talking about the shape function. I'm talking about the values of u and v at A and B. So values of u and v at node A and B would be same, but the shape functions could be different. I mean, form of the shape function could be different.
Yes, sir. Thank you, sir.
Okay. So now let's talk of a rectangular element. So it would be a 4 noded element. So this is say x and y. These are the nodes 1, 2, 3, and 4. And now the four and each node, because one requirement is that primary variables should be there as degrees of freedom at the node. So that is a must. So like the coordinates would be x1, y1, and the degrees of freedom at this node would be u1 and v1, and similarly other nodes x2 y2 and u2 v2 and so on. So now in this case, if you look at the approximate solution, so this is now I'm talking about four noded rectangular element. Rectangular element. So in this case, the approximate solution u will be now see there are now four nodes, and each node we have u as a degree of freedom, v as a degree of freedom. So total we will have four unknowns in the element corresponding to u, four unknowns in the element corresponding to v. So we should have same number of unknown constants in the approximate solution. So here we assume an approximate solution with four terms. So a0 plus a1x plus a2y and then plus a3. Now next term, what we have already linear term in x, linear term in y. So next option is either we can go for x square or y square or xy. So but we go for xy because that is geometrically invariant. If we take x square and if interchange x and y, the form is going to change, so it will not be geometrically invariant. So we take the fourth term as xy. So similarly v will be taken as b0 plus b1x plus b2y plus b3xy. And of course again no, you express a0 a1 a2 a3 in terms of u1 u2 u3 u4, b0 b1 b2 b3 in terms of b1 b2 b3 b4, and then put the approximate solution in the integral functional and get the element level governing equation. So let's check the compatibility condition. So now we are let us say we have a domain. I may discretize this into, let us say, four elements. So this is element 1, this is element 2, and let us say this is 3 and this is 4. And now if you see again, when we talk of common boundaries, say you can take any common boundary. Let me take this AB. So along AB, and let us say here this is x and this is y coordinate. So along AB, your y coordinate is constant. So if you look at line AB in this case, line AB. So along line AB, if you see here, we have y is equal to constant. If you look at the let's say line BC, then you will have x is equal to constant. So you can have a similar argument. So now along line AB, y is constant. So if y is a constant, then if you look at the variation of u along AB, so it would be a0 plus a1x plus a2c plus a3cx. So you can write this as a0 plus a2c. These are constants, and then you have a1 plus a3c into x. So you can again see that the variation of u and similarly v would be linear in x, and at a and b already the values of u and v are common between the element 1 and 3. So both element 1 and 3 at a have same values of u and v. Because u and v are the nodal degrees of freedom, during the assembly we take same u and v whether the node a is belonging to element 1 or node a is belonging to element 3. So similarly at v. So again the variation, that means variation of u along AB is linear in x. Similarly variation of v along AB would be linear in x, and at a and b already the values of u and v are common for both the elements. So we will again get a unique variation. So we will have same values of u and v along AB whether calculated from element 1 or calculated from element 3. So you can say that this element is also compatible. But important thing here is that basically the element is a rectangle. Now let us talk of a four noded quadrilateral element. So general quadrilateral. So now when you have a general quadrilateral, it's also four noded quadrilateral. So the solution form is going to be same xy, the four nodes. I'm still talking about the four noded element. So this is node 1, this is node 2, this is node 3, this is node 4, and the solution will be same of what we have assumed for the rectangular element. That is, in this case also, the when you look at the approximate solution, it would be a0 plus a1x plus a2y plus a3xy, where now of course the a0, a1, a2, a3 are constants. Similarly, v will be b0 plus b1x plus b2y plus b3xy. Now whether it is the compatible or not, so that is what we want to look at it. So now when you look at the compatibility, so let us say again I have a domain and I discretize this into quadrilateral elements, not the rectangular elements. So that means I discretize this is something like this. So let's say one element is here, another element here, third element is like this. So this is element 1, this is element 2, this is 3, and this is 4, and these are the nodes. So we discretize this domain using this kind of elements. And now so let me look at the any one boundary. So let us say this I take AB, and this AB is shared by both elements 1 and 2. So whether we have same variation of u and v along AB or not from element 1 and 2. If they are same, then it's compatible. If it is not, then this will not be compatible. So now if you look at again line AB, so if you look at this line AB, the equation of line AB would be when we move along line AB, let us say y will be mx plus c. So now if I look at the variation of u or v along AB, so let us say u along AB would be equal to a0 plus a1x plus we will have a2 into y is mx plus c, and plus we will have a3 into x into mx plus c. So now if you look at, you can see that the constant terms are a naught plus a2 into c. These are the constant terms. Then terms linear in x are a1 plus a2 into m plus a3 into c. So that is x, and then plus we have this a3m into x squared. So in this case, what you are getting is, no, u along AB is quadratic in x. Whereas no, we have only two values of u common at A and B. So when we get the variation of u along AB from element 1, because it is quadratic and only the values at A and B are common, so the variation of u along AB from element 1 would be different from what we get from element 2. So if it is not same u along line AB, then the element is not a compatible element. And if you know if you have the element which is compatible, then your solution will always converge from no, it will give you always a basically the the lower bound. So it will converge from lower side. The displacement will increase from a lower value to higher value when you increase the number of elements if the element is compatible. But if the element is not compatible, then it will give you oscillatory behavior with increase in the number of elements. So judging the convergence is difficult in case of that kind of elements. So now here what I am saying is, now if I look at the variation of say u along AB, and this is the say length along line AB. So at 2 point node A, let us say this is A, and then at B, at these two locations u and v are same from whether we talk of element 1 or element 2. But in between, since the variation is quadratic, so it is expected that say element 1 will give you this variation, and maybe element 2 might give you some this kind of, I mean, that also is a non-linear, not linear. So that gives you, let us say, some variation like this. So this is from element 2. So although at A and B the u values and similarly the v values are same, but in between between A and B, the values of u from A element 1 and 2 are not same, they are different. So the element would be incompatible. So this is incompatible element. So now you might be thinking that no, if you use the quadratic element, So that means instead of 4 noded, if you go for an 8 noded element, so that means you introduce the nodes at all the boundaries. So when you assume approximate solution, you will get quadratic. And in that, when you substitute the equation y equal to mx plus c, it would become cubic. So again, although there are three values common, but then based on three values, we cannot fit a common curve which is cubic. So whatever you do, if you keep on increasing in the number of nodes, the element will not become compatible if it is a quadrilateral element, arbitrary quadrilateral. So that is why there is a need for formulation in the natural coordinate space. So the physical geometry of the element can be any arbitrary quadrilateral, but if it is formulated in the natural coordinate space, then the element will always be compatible. So that is why there is a need to formulate the element in natural coordinate system. So when you are doing the natural coordinate, means the coordinates are varying from -1 to +1. So natural coordinate system formulation. So in this, what we do is in the the element in the physical coordinate space, that is xy space, is arbitrary quadrilateral. And let us say we take 4 noded, so 1 2 3 and 4, this is the element, and these are the x and y coordinate. But this element is mapped to square in the natural coordinate space. So we have the square in the natural coordinate space. So we now the natural coordinates are, let us say, xi and eta, and the nodes are, so node 1 in the physical coordinate space is mapped to node 1 in the natural coordinate space, node 2 in the physical coordinate space is mapped to node 2 in the natural coordinate space, similarly node 3 and node 4. And if you have any point here xy, that would be corresponding to some point here xi and eta. So now instead of assuming the approximate solution in terms of x and y in the natural coordinate formulation, we assume the approximate solution in terms of natural coordinates xi and eta. The nodal coordinates you already know that these are x1, y1, x2, y2, and so on. Here the coordinates are, this is -1, xi is -1, eta is -1, this is 1, -1. So the natural coordinates are varying from -1 to +1. This is 1 comma 1, and this is -1 comma 1. So now if you assume the approximate solution in terms of the natural coordinate system, so now that means, say you will be assuming u is equal to a0 plus a1 xi plus a2 eta plus a3 xi eta. Similarly, v will be assumed as b0 plus b1 xi plus b2 eta plus b3 xi eta. Now see, because we are assuming the approximate solution in terms of natural coordinates, and in the integral functional we have to carry out the integration with respect to physical area of the element in the physical coordinate space, and also strain require the derivative of displacement with respect to x and y. So we need to relate xy in terms of xi eta. So we also assume the solution for x and y. So c0 say plus c1 xi plus c2 eta plus c3 xi eta, and y will be equal to, say, d0 plus d1 xi plus d2 eta plus d3 xi eta. And now if you see, these are the field variables. So u and v are the field variables, and x, y are the physical coordinates, x and y geometry. So both are interpolated using same kind of polynomial. So this formulation is also known as isoparametric formulation. So if the interpolation of field variables u and v is same as the interpolation of physical coordinates, that is interpolation of geometry, that is xy coordinate, then it is known as the isoparametric formulation. So I will be, of course, discussing how do we get to the the formulation, development of the element level governing equation from here. But for the timing, let me again talk of the compatibility condition, whether now this element is compatible or not. So in the physical domain, let us say we have a domain and we discretize that into arbitrary quadrilaterals. So when we discretize this into arbitrary quadrilateral, so we have let us say quadrilateral element like this. So this is the discretization. And now if you look at, these are, say, this is element 1, this is element 2, this is element 3, this is element 4. And let me take this let us say line, let me take any line. So let me take this line AB. So between elements 1 and 3, see, this is the geometry in the physical coordinate space. So this is X and this is Y, but all these elements, all the 4 elements would be mapped to a square in the natural coordinate space. So we'll have xi, we will have eta, and these would be 4 nodes of that element, local node numbers 1, 2, 3, and 4. So now when I look at along AB, so no line AB, if you look at along line AB, you are going to have, now when we are talking of AB, so let us say, when we talk of element 1, this node is mapped to node 1 of the element in the natural coordinate space. This is mapped to node 2, this is mapped to 3, and this B is mapped to 4. So no, that means AB would be corresponding to edge 3, 4 in the natural coordinate space. And when we talk of no element 3, let us say A is mapped to 1, B is mapped to 2, and then this is mapped to 3, and this node is mapped to 4. So AB of element 3 would be corresponding to edge 1, 2. So whether we are in element 1 or element 3, in both cases either we are moving along edge 1, 2 in the natural coordinate space, or edge 3, 4, and in both cases you will see that eta is going to be constant. Along edge 1, 2 eta is constant, along edge 3, 4 is eta is constant. So line along line AB would have eta is equal to constant, and that is either plus 1 or minus 1. So if eta is constant, so now if I look at u along AB, so u is going to be now a0 plus a1 xi plus a2 into c plus a3 xi into c. So you can see that this is a0 plus a2 into c, and then we'll have a1 plus a3 into c into xi. So you can see that the variation of u along line AB, whether we are going from element 1 or we are going from element 3, it is linear in xi. And at A and B, because no, the degrees of freedom are common between element 1 and 3, so in between the variation is linear, so it would be unique. So when we are moving along line AB, you will see that we are going to get a unique, I mean the same variation of u along AB, whether we get it from element 1 or element 3. Similarly, we will get same variation of v along AB, whether we get it from element 1 or 3. So now if you look at the basically, when you talk of u along AB and along when we move along the, so when you are moving along AB, if you are in element 1, you are basically moving along edge from the basically 4 to 3, and if you are moving along AB in element 3, then you are moving from 1 to 2. In both cases, eta is going to be constant, so the uab is going to be linear function in xi. So if it is linear and at A and B the values are already common, so we will get the same variation, so from A to B. So whether we are getting from element 1 or element 3, we will get the same values of uab, and therefore it would be compatible.
Excuse me, sir.
Yeah.
So actually, we are mapping a physical coordinate into a natural coordinate system. So in the natural coordinate system, we are taking the origin of the coordinate to be at the centroid of the square element.
Yeah, right.
So why we are doing this? Like for the case of simplicity, or there is something logic behind it? Sir, I didn't get
No,
that.
yeah, there is no in that there is no logic. Yeah. So it is
So
no, it is for the simplicity. In that, there is also natural coordinate itself is defined, as a coordinate varying from -1 to +1, and that is why we are taking that. So as long as you map this physical element in the physical coordinate space to a square in the any space in the square, the same square, and square should be same. The sizes of the square should be same. So it will always give you the compatible element. So by here, of course, by choice we are using the natural coordinate which are varying from -1 to +1.
Okay, but suppose if we are taking any arbitrary mapping, and if we keep the like the side of the element to be parallel to the coordinate axis, in that case also the element will come to be compatible, right,
Yeah,
sir?
right. That's correct. Yeah, right, right.
Yeah, so means we can do that also.
Yeah, we can do that. Yes, we can do that. But the advantage is that for the natural coordinates, when we finally evaluate the matrices, so the the integration points, Gauss quadrature numerical integration points are already available. Of course, we can always convert from there to any other coordinate of same type. But yeah, the basic idea is that we should have mapping to a square in the natural in the other space, and as long as we do that, we will have a compatible element.
Thank you, sir.
So I think yeah we have. So let me this is what I wanted to emphasize. So basically, no,
Hello.
the why go for the formulation in natural coordinate space, so that even if the element is arbitrary in the physical coordinate space, it satisfies the compatibility condition. And so compatibility conditions, the satisfaction meaning that it will give us the monotonic convergence, and that is why we go for the formulation in the natural coordinate space for the 2D and 3D problems. 1D problems, of course, can be either formulated in the physical coordinate or natural coordinate space. Yeah, somebody was asking something.
Hello, sir.
Yeah,
Sir, in natural coordinate system, discretization is will be always be square.
yeah, in the nature, because all the elements in the physical coordinate space are mapped to the same square in the natural coordinate space. So it is always going to be square of side length 2, because the coordinates are varying from -1 to +1, so the side length is 2. So all the elements in the physical coordinate space are mapped to the same square in the natural coordinate space. So that is why this element, in the natural coordinate space is also referred to as master element.
Okay, so it means whenever we will random discretize, it will always be square element.
Yeah, yeah. In the natural coordinate space, it will always be square. Although in the physical
Oh,
coordinate space, this is arbitrary quadrilateral.
okay, okay.
So now the other step. So let me also, since I have taken this element, so briefly tell you. So once we have done this, what we do is we want to express the unknown constants a0, a1, a2, a3 in terms of values of your variable u at nodes 1, 2, and 3. So we will write no yeah, we need to express a0, a1, a2, a3 in terms of u1, u2, u3, and u4. So how do we do that? So we say that u1 is the value of u at node 1. So if I write in the matrix form, I can say that u1, u2, u3, u4, these are the values of u at node 1, 2, 3, and 4 will be equal to this side. Now we have let us say a matrix, and the constants a0, a1, a2, and a3. So we write u is equal to 1 zeta eta and zeta into eta vector into a vector a0, a1, a2, a3. And then at node 1, since zeta and eta both are -1, so we will get 1, -1, -1 and +1. At node 2, zeta is no, not zeta, xi. No, this that letter is actually xi, so I'm using xi and eta. So xi would be +1, eta is -1, so we will have 1, -1 and -1. At node 3, xi and eta both are +1, so we will have this as 1, 1, 1. And lastly, u4 would be at node 4, xi is -1, eta is +1, so we will have 1, -1, 1 and -1. So from this, let us say if I call this as some matrix A and this as matrix small a, so this is A and this is small a. So you can say from this that small a, which is a0, a1, a2, a3 would be equal to A inverse into this vector u1, u2, u3 and u4. So finally you can say now that u, which is written as say 1 xi eta and xi eta into a0, a1, a2 and a3. So this can be written as basically 1 xi eta and xi eta into A inverse into u1, u2, u3 and u4. So then what you can say finally that u is equal to, now if you multiply this this vector with A, so if you look at, this is 1 by 4 vector, this is a 4 by 4 matrix, and this is 4 by 1. So when you multiply these two, 1 xi eta, this and A inverse, it would be 1 by 4. And let us say those are no n1, n2, n3 and n4, and then into you have this u1, u2, u3 and u4. So these n1, n2, n3 are known as the shape functions or the interpolation functions. And in this particular case, they are also basically the Lagrange interpolation functions. So where your n1 would be equal to, when you multiply this 1 xi eta with A inverse matrix, you will get n1 as 1 upon 4, and then you have 1 minus xi into 1 minus eta. And similarly, n2 would be 1 by 4, 1 plus xi into 1 minus eta. And n3 would be 1 by 4, 1 plus xi into 1 plus eta. And n4 would be 1 by 4, 1 minus xi into 1 plus eta. So these are the shape functions. If you look at, so now u can be interpolated as n1 u1 plus n2 u2 plus n3 u3 plus n4 u4, where n1, n2, n3, n4 are given by these. And if you look at the, because these shape functions are defined, n1 is defined at node 1, n2 is defined at node 2, n3 is defined at node 3, and n4 is defined at node 4. So this is xi and eta. So we will find that n1 is going to be unity at node 1, and it would be 0 at node 2, 3 and 4, and actually it would be 0 along edge 2, 3 and along edge 3, 4. Similarly, if you look at n2, would be unity at node 2, because if you put the coordinates of node 2, that is xi as 1 and eta as -1. So when you put here, you will get this as unity. So n2 would be unity at node 2, 0 at node 3 and 4, 3, 4 and 1. So it would be 0 along the entire edge 3, 4 and 1, 4. Similarly, n3 would be unity at 3 and would be 0 at node 1, 2 and 4. Similarly, n4 would be unity at node 1, node 4, and will be 0 at node 1, 2 and 3. In fact, it would be 0 along edge 1, 2 and edges 2, 3. So that means similarly you can say that u can be written as summation ni ui, where I going from 1 to 4. V can be written as I going from 1 to 4 ni vi. Similarly, the coordinates x can be written as summation I going from 1 to 4 ni xi, and y can be written as summation I going from 1 to 4 ni into yi. Only difference in this interpolation is that ui and vi are the unknown quantities, whereas the xi and yi, which are the x and y coordinates of ith node, they are known quantities. So now you have same kind of an interpolation. Now the next step, what you do is you write this both u and v together. So vector uv will be can be written as in the form together, and this side you will have the vector of elemental degrees of freedom. So when we put no all together, u1 v1, u2 v2, u3 v3, u4 and v4. So when we put all of these together, so we will have u as n1 0, n2 0, n3 0, n4 and 0. So that no you get n u as n1 u1 plus n2 u2 plus n3 u3 plus n4 u4. Similarly, v will be n1 v1 plus n2 v2 plus n3 v3 plus n4 v4. So as per the we call this as the interpolation matrix H. So this is H, and the other vector, this is referred to as DE. So H is known as the interpolation matrix. Interpolation matrix, and DE is the vector of elemental degrees of freedom. Vector of elemental degrees of freedom. Okay, so now this is u and v are written as in terms of h and de in terms of the shape functions. Now we also require strain. So epsilon is equal to nothing but your epsilon xx, epsilon yy, and gamma xy. So these also we want to write in terms of derivatives of the shape functions and the dE. So let me write this as dE. So epsilon xx is del u by del x, and del u by del x can be written as del n1 by del x into u1 plus del n2 by del x into u2, so and so on. So you can write this as del n1 by del x 0, del n2 by del x 0, del n3 by del x 0, del n4 by del x 0, and similarly epsilon y 0, del n1 by del y 0, del n2 by del y 0, del n3 by del y 0, del n4 by del y, and gamma xy would be del u by del y plus del v by del x. So it would be del n1 by del y into u1 plus del n1 by del x into v1 and plus other terms. So you can write that as del n1 by del y, del n1 by del x, del n2 by del y, del n2 by del x, del n3 by del y, del n3 by del x, del n4 by del y, del n4 by del x. So you can write like this. And so in the notation we call this as B and into DE. So this is your B, and B we call it as strain displacement matrix. Strain displacement matrix. So now you substitute all of these in the integral functional. So you substitute all of these now, these approximations in the integral functional. So you will get your I now. I, if you look at I, can be written as half integration over area H, and then we have epsilon transpose. Epsilon is B into D. So we will get here D transpose into B transpose, that is epsilon transpose, and then we have C constitutive matrix, and again epsilon, so that will give you B into DE dA, minus we will have the integration over area H, and then we will have D transpose, we have UV transpose, so D transpose into H transpose into FBX FBY dA, minus we have integration over boundary, So UV, so again DE transpose into H transpose into TX TY DS. So this is your I. Now for equilibrium, we have this delta of I equal to 0. So when you write the expression for delta of I, so as I have told you in the 1D problems, you can write the delta of I as delta of, and D can be taken out of the integration sign. So we can write it as delta of D transpose, and then we have this integration over area H into B transpose into C into B dA. So this will be into D minus, I am taking delta D transpose common throughout. So we will have minus this integration over area H into this H transpose into FBX FBY dA minus integration over boundary H transpose TX TY DS. This is equal to 0. So now this we get delta I, and this is equal to 0. Now this, since delta DE is arbitrary, so we get, then the equation we get, which is of the form this KE into DE is equal to, now AF has got two portions, so let me say AF B for the element and FT for the element. So this is the element level governing equation, where Ke is the element level stiffness matrix, which is nothing but integration over area H into B transpose into C into B into dA. And then what you do, because now if you look at B, these are in terms of the derivatives of the shape functions, say n1 n2 and so on. So B will be function of xi and eta. So that means the quantity which we are integrating is a function of xi and eta. So this integration we write in terms of xi and eta. So integration -1 to +1 -1 to +1 H into B transpose into C into B into determinant of the Jacobian matrix into d xi into d eta. This is your K. I have not, I presume that you have, or I think I can do the Jacobian in the next class. How do we get this Jacobian? The concept of Jacobian, but no, you get this as your stiffness matrix. Similarly, the load vector FBE for the element would be integration from -1 to +1, integration from -1 to +1, and it would be H into H transpose into FBX into FBY, determinant of J into D xi into D eta. And so similarly, no, of course, the other integral I am leaving as it is because that's the boundary integral. So you write the the element level governing equations like this, and then of course you have to do the assembly, impose the boundary condition, and solve the problem. So I think that is where I want to stop. If you have any questions, you can ask. So next class I will be actually starting with the plate bending element. So that's the next the topic, which is going to be a new topic. So far whatever I have discussed, it's more like I expect that some or the other form you would have done all of these things in the basic FEM course. So far I am thinking as if I am revising what you would have already done. But if you have any questions, you can ask. Yes, hello. Anybody? Any other question?
Hello, sir. Hello.
Yes, please.
Sir, if we'll means formulate the shape function for the second matlab B, then if we follow the same procedure, then
Yeah,
we'll get the same. We are now doing the only one eta jhai and eta jhai. That things we are doing for same functions.
yeah.
Then if we will calculate the same function for v also, then we'll end up same formula or
Yeah, we will
different.
get the same thing. We will get the same thing because see, V is also interpolated in a similar manner. So
Yes,
you
sir.
will get V equal to 1 jha eta and jha eta into B0, B1, B2, B3. And then
Yes.
you write the same expression V1 is equal to V2 is equal to V3, V4. So you will get same form of the matrix A and its inverse into no 1 jha eta into jha eta and A inverse will be same. So you will get the same shape functions for U, same shape functions for V, same for X, same for Y. So all are same. So if you see, I have, that is how I have written here. No? If you see here, I have written the same shape function. No, NIUI, NIVI, NIXI, NIYI. So same shape functions are going with UV, X, and Y.
Okay, sir. For x
Yeah.
and y also same.
Yeah, for X and Y also it is going to be same. Of course, this is isoparametric formulation. If we are using subparametric or superparametric formulation, then say functions for x, y would be different from the say functions for u and v.
Okay.
Yeah,
Okay. And sir, another question is in next page. In next
yeah,
page. In next page, sir, you are writing in matrix form that dn1 by dx, but dn1 by dx, dn1 by dy means delta, but
yeah,
n1 and n1 is a function of r and means zeta and
yeah,
eta,
yeah,
jhai and eta.
yeah.
Then how we will calculate these things? Means partial
Yeah, so
derivative
for
like
the
that.
calculation of that, yeah, we have to use the Jacobian matrix and its inverse. So
Okay.
if you, yeah, for that, no, the concept of Jacobian matrix is needed. So I
Okay.
think I have some time. So since you asked that question, let me explain that. So suppose
Okay.
if you have some function of f, let's say f is a function of x and y, and we want its derivative, let us say, because x, y are related in terms of xi eta, so f can also be expressed in terms of xi and eta. So we can also write this as a function of xi and eta. So now if I want the derivative of f with respect to xi, assuming that f is explicitly expressed in terms of x, so I can write an x is a function of xi and eta. So I can write del f by del xi as del f by del x into del x by del xi plus del f by del y, and y is a function of also xi, so del y by del xi. Similarly, you can write the del f by del eta, so as del f by del x by del eta plus del f by del y into del y by del eta. So now from this what you can do is, if I just take the operators, so I can say del by del xi and del by del eta is equal to, now this side I have del x by del xi, del y by del xi, and del x by del eta, del y by del eta into the operators del by del x and del by del y. So you have this relationship. In this, no, this is called the Jacobian matrix J, and into of course del by del x and del by del y. If you pre-multiply by the J inverse, so you can see that you can write actually no del by del x and del by del y, the derivative operator with respect to no x and y can be written as no this J inverse into del by del chi del by del eta. So you can write it like this. Now J is a 2 by 2 matrix for 2D problems, and let us say its inverse is J11 star, J12 star, J21 star, and J22 star. So if you take the inverse, the values are given by this del by del chi del by del eta. So now if you take the del by del x, you can say is nothing but J11 star into del by del xi plus J12 star into del by del eta. Similarly, del by del y is J21 star into del by del xi plus J22 star into del by del eta. So now if I write del ni by del x, the derivative of ISA function, I can write that as J11 star into del ni by del xi plus J12 star into del Ni by del eta. So since the shape functions are expressed already in terms of xi and eta, so I have those expressions, and then I can get the derivatives with respect to x. Similarly, del Ni by del y will be written as J21 star into del Ni by del xi plus J22 star into del Ni by del eta. So from these we'll be able to get the derivatives of the shape functions with respect to x and y. So is that clear?
Yes, sir. Thank you.
So are there any other questions? Anybody, any other question? So if there are no questions, I am stopping here. Thank you all for your attention.
Thank you, sir.
Anybody wants to ask any question? If there are no questions, I am stopping. Thank you all for your attention.